Hi there, folks. Today we are going to finish off the Math 355 material. So we are going to be covering the last few sections of Chapter 7, including separable equations, systems of differential equations, and phase plane analysis. We're also going to be throwing in a section from a different textbook, an old differential equations textbook, Boyce and DePrima. Mostly it's so that we can see a different type of differential equation. Basically, there's a lot of different methods for solving differential equations. Your textbook really only explores a couple, and there's one big one which is skipped. And so I wanted to make sure that we at least see that. I don't think it'll be in your online homework, but that's okay. But really what today's about is it's about showing you the phase diagram, the phase portrait. Show you how we can start analyzing multiple differential equations which are going on at the exact same time, as well as give you some techniques for solving differential equations. Up to this point, we know how to solve pure time differential equations, but we don't really have any techniques for autonomous differential equations or non-autonomous differential equations. And that could be very, very useful. And so we're going to introduce you to a few techniques, and then we're going to be talking about how to do multiple differential equations which are going at the same time. And this is a very important subject when we're thinking about biology and medicine. We've talked in the past about how everything can be modeled using differential equations. Well, it's usually not going to be a single differential equation. You cannot model the entire universe using a single differential equation. Instead, it's a number of differential equations which model different things and how all of these differential equations interact with one another. Take, for instance, the predator-prey model, which we'll be seeing later. The predator-prey model shows how a population of predators and a population of prey interact with one another. And using that model, we can come up with some decent estimates for what populations will be at different times. Of course, it's not a closed system. And so there are external factors which are going to affect things. But trying to understand all of the different external factors which affect a system can create a closed system. And once you have a closed system of differential equations, you can start to analyze them. In many of the online articles you might be looking into right now related to the mathematics of your field, you might be finding these differential or these systems of differential equations, and they've tried to create models which are closed systems. That's really the goal as a biology or medical researcher. You want to create a closed system model so that you can understand everything that is affecting your particular interest. That said, we're also going to be looking at parametric equations and how we can use them to understand systems of differential equations. Take, for instance, this differential equation right here. This is x prime of t is equal to y times x squared minus 1, and y prime of t is equal to x plus 1. This is a system of differential equations, and notice that it's autonomous in that it has no time variable involved in it. X prime is a function of x and y prime is a function of x and y. But these are functions of t. When we're looking at rates of change with respect to t, basically it's telling us what the slope is at that particular time. But since we're thinking of these as two different populations, we can actually show how these populations are transforming with respect to time. And that's what this graph is representing. We'll learn the fundamentals of how to graph something like this later today. Your homework, I believe, focuses more on the idea of null lines and how to plot and understand null lines. Doing graphs in as much detail as this is really something which occurs in chapter 10. And in chapter 10, you'll be able to do much more analysis because chapters 7, 8, and 9 are all building up to the idea of understanding models like this. And also, welcome to the world of chaos theory. We've said it before, we'll say it again. This is really what chaos theory is about. Chaos theory is about understanding how a small change in initial conditions can have drastic changes in results. And in a system like this, depending on where you start on this graph, where you end up is going to be wildly different. That said, let's start with some simple differential equations which we can solve. And we'll start with this one right here. dy dt equals y times t plus 1 and y of 0 equals 2. This is a separable differential equation, and it's also an initial value problem because we have this initial value. And so let's see if we can actually solve this one. I'll stop the share so that we can bring the whiteboard on up. So it is dy dt is equal to y times t plus 1. And y of 0 is equal to 2. This is the initial condition that we're given. And so when we look at this, we can't just integrate. Before, when we had a derivative, if we wanted to solve, we could just integrate, but that only worked for pure time differential equations. This one is a function of both y and t. And it might not be obvious how we can go about solving this. Now, there is a physicsy way of doing this, in that this, this derivative right here, dy dt, can be thought of kind of like a fraction. And that's really the way that a physicist might approach this. A physicist might take this and say, well, this is a fraction. We could cross multiply the dt up here, bring the y over to the left side, and then just integrate straight away. And it turns out that works. There are many reasons as to why that works, mostly related to how the chain rule works. But for our purposes, we just need to be able to actually calculate something like this. If we want to, we can multiply and divide on both sides to try and separate this differential equation. And that's why this is called a separable differential equation. In this case, if we cross multiply, we can bring our dt up. So we'll keep our dy on this side. And we'll have the y times t plus 1. And we'll have a dt there. We can also bring the y over to the left side just by dividing, which will give a 1 over y dy. Now notice the left side is nothing but y terms, and the right side is nothing but t terms. At this point, we are able to integrate. Integrating the left side, well, the integral of 1 over y is going to be equal to the natural log of y. Yeah, natural log. Technically, it's a natural log of absolute value of y, though often when we're doing differential equations, we'll just drop the absolute values because we're only interested in positive populations. And so we'll drop those absolute values for now. Depending on what you're doing, you might want to keep them. On the right side, we're going to have the integral of t is going to be 1/2 t squared. And the integral of 1 is going to be equal to t. Now, something you might notice is missing from both sides is a plus c term. Because when we integrate this, we would get a plus c. And when we integrate this, we would also get a plus c. We would not want to put a plus c on both sides because the constant on the left side and the constant on the right side would likely be different constants. And so instead we could do a plus c1 and a plus c2. But if we subtracted one of the constants over, we would end up with just a single constant. And so what you'll often see is you'll just see a single constant carried on throughout this. Now, this constant is actually going to change and do some interesting and weird things. And so maybe we will just label this C0 for now, and using a little subscript of 0 to represent that this is just our starting point with this constant. This constant is going to have some weird things happen to it. Because now, if we want to actually solve this equation, we would need to get rid of this natural log. And the way we can get rid of that natural log is by doing e to both sides, which would give us e to the natural log of y is equal to e to the 1/2 t squared plus t plus c naught. The left side now becomes y. The right side is going to become e to the 1/2 t squared plus t plus c naught. But if you remember from algebra 2, if we have e to the a plus b, we can rewrite this as e to the a times e to the b. Well, we can do the same type of thing here. And so in this case, we have an e to the 1/2 t squared plus t plus c naught. We can actually separate this c naught out, which would give us an e to the 1/2 t squared plus t times e to the c naught. But notice e to the c naught is just going to be a constant again. And because it ends up just being a constant again, we can actually just relabel this as some new constant. Let's call it C1. So then we have y is equal to C1 e to the 1/2 t squared plus t. This right here, we would call the general solution. And if this were not an initial value problem, we would be done at that point. This is what the solution would look like for this differential equation. However, this is an initial value problem. And so we can go further. In fact, we can solve this because we know that y of 0 is equal to 2. And so we can take this equation and we can take this initial value and we can plug them in. And so y of 0 is equal to 2 tells us that 2 is equal to C1 e to the 1/2 of 0 squared plus 0. I'll throw parentheses around that too. Well, that's e to the 0, and e to the 0 is just 1. And so that tells us that our C1 value is equal to 2. Well, now that we have C1 is equal to 2, we can plug that in here and get our particular solution. And so y is equal to 2 e to the 1/2 t squared plus t. And again, this is what we call the particular solution. The general solution tells you what all of the solutions for the differential equation will look like. The particular solution tells you what the particular solution to this differential equation is when we have this particular initial condition. And that's really the distinction between these. If you are given an initial value or an initial condition, then you have to go all of the way out to the particular solution. If you were not given this initial condition, we could stop at the general solution. And if you would like, I actually have this one worked all of the way out in the notes. Let me pull the screen back. Here we go. Share screen. And this one's worked out here. And so notice we started with a dy dt equals y times t plus 1, and y of 0 equals 2. After working through this entire problem, we ended up getting y equals 2e to the 1/2 t squared plus t, which is what we ended up having. A differential equation which can be broken up in this matter is called a separable differential equation. Of course, not all differential equations are separable, and that's one of the challenges. This separable approach is really the easiest one out there, next to just integrating straight away for a pure time differential equation. But this separable differential equation strategy is kind of outlined here. Dy dt, if you're given dy dt is equal to a function of y times a function of t. And really, it has to be a product, or it could be a quotient, but really we have to have the terms multiplied by one another. If they are added to one another, we probably are not going to be able to use the separable approach. Because the first step is to get all of your y's on one side. And this term, this 1 over fy, needs to be multiplied by this dy. The reason for this, and why we're actually allowed to separate this up, the dy and the dt terms are considered differentials. I don't think we covered that idea of what a differential is in this course, but really we can think of this as an extremely small change in one direction. And so dy would correspond to an extremely small change in the y direction, and the dt would correspond to an extremely small change in the t direction. And then when we do the integral, we're adding up the product of our height, which is given by the function here, times our dy, which would represent our distance in the y direction. And so it's basically a base times height, and then we're doing an infinite summation over them, which is what the Riemann sums were all about. But what we're doing here is we're saying that we can cross multiply and get our dy's on one side, our dt's on the other side. Then we integrate both sides with respect to the variable, and don't forget the plus c. You don't need to put it on both sides, but you do need to include it on one of the sides. Then solve for y, if possible. It's not always going to be very nice or very possible, and so sometimes you'll just keep it as is. And then solve for any unknown constants if possible. And that's where, if it were an initial value problem, we could solve for whatever constants we have. Here's the practice problems. Don't know that we'll do all of them, but we'll do a few of them. And we might even just start by looking to see if we can do them. Not all of these are separable. So looking at the first one, dy dt plus y equals 1. This one is very separable. It might not look it at first because notice we do have the sum in there, but what we can do is we can move that y over to the right side, and then we can separate it out. And so let's try this one. This is a nice, easy one. Dy dt plus y equals 1. So what we can do is we can shift the y over to the right side, giving us dy dt is equal to 1 minus y. And then we can cross multiply, basically bring the dt up and bring the 1 minus y down, which will give us a 1 over 1 minus y is equal to, oh, I forgot my dy, is equal to 1 dt. And now we need to integrate both sides. When we integrate the left side, we're going to get a natural log of absolute value of 1 minus y. And I believe we will also get a minus sign that comes out of it from the chain rule. There's an easy way to check this. If we were to take the derivative of this, the derivative of natural log of stuff would be 1 over that stuff, so 1 over 1 minus y. But then the derivative of 1 minus y would give us a negative 1. So we need that negative out there to balance it out. Equals, and then it's going to be t dt. Oh, sorry, no dt there. The integral of 1 dt is t. And then we have our plus c. Now, depending on how we go, we could drop these absolute values. We don't have to. It really depends on which region we're talking about. For our purposes, let's keep the absolute values in there and see what happens, because that might be an interesting thing to explore. And so to solve this for y, we might start by moving the minus sign over to the right side, which would give us a natural log of absolute value of 1 minus y is equal to negative t. And here's a fun bit. Remember how this constant can be a changing constant? If we think of this as c naught, we could make this be c1 and actually keep this as a plus sign, where we would say that c1 is equal to negative c naught. To get rid of the natural log, we would need to do e to both sides. And doing e to both sides, we would get the absolute value of 1 minus y is equal to e to the negative t plus c. But if you remember, this c1, and when we have an e to the c1, we can actually bring that out and make a new constant out of it, which would make this a c2 e to the negative t. Now, to get rid of the absolute value bars, remember when we have an absolute value, it really just makes it so that the right side is always positive. And so this absolute value bar could really just be removed because this C2 is going to absorb any negative signs that pop out of this, which leaves us with 1 minus y equals C2 e to the negative t. If C2 is positive, great. If C2 is negative, great. But now we can clean this up by just bringing our 1 over and then changing the signs of everything. And so if we subtract 1 on on both sides, we'll get negative y is equal to C2 e to the negative t minus 1. And then our last step is we need to add or change the sign of both sides, which would give us a y equals, and now again, we could change the C2 so that it absorbs that minus sign, C3 e to the negative t plus 1, because we would have to change that sign. And now for our final answer, let's drop that 3 and just call this c e to the negative t plus 1. And that is our solution, our general solution. Hopefully that process made sense. It's kind of a tricky thing when we start dealing with these constants. And I think that's where a lot of folks struggle, as well as how to deal with absolute values. But often in differential equations, we just drop those absolute values because we're only looking at positive populations to begin with. Let's check out another one. So number 2 is much, much easier. Really all we would have to do is just cross multiply, and we would have all of our y's on one side and all of our x's on the other side. For 3, same exact thing. We could cross multiply. And here I'll zoom in a little bit so we can see it a little easier. That might be too far in. There we go. And so for number 3, it's going to be exactly the same. We could cross multiply our cosine up, cross multiply our dt up, and then integrate both sides. 4 is much more interesting because 4 we cannot do. And so 4 is not a separable differential equation. If we moved the y over to the right side, there's no way that we could separate the y and the t using multiplication. If you have a t minus y, it's just stuck there. And so we would not be able to use this technique to solve number 4. 5 is also separable. We just move the 3y over, and then we could bring the t plus 1 dt over, and then we could bring the 3y plus 5 over and integrate. Let's do an initial value problem. Let's do number 1 for this initial value problem, just so that we can make sure we know how to do it. So the initial value problem is dy dt equals t squared plus 5 over 2y minus 1. And y of 0 is equal to 11. Cool. And so in order to do this one, what we would need to do is, again, just separate everything out. And so when we separate everything out, we are going to get a 2y minus 1 dy equals t squared plus 5 dt. And we're just integrating on both sides. On the left side, we can integrate. We're going to get a 2y goes to y squared minus y equals, on the right side, it's going to be a t cubed a 1/3 plus 5t plus c. Now, solving for y in this case is not going to be very practical. We could do it, but because it's a quadratic, we would end up getting pluses and minuses everywhere. And so we might just keep this equation as is and say that this is the general solution. But we can still figure out what the c value is because we have an initial condition. And so using the initial condition, we would say that 11 squared minus 11 is equal to 1/3 of 0 cubed plus 5 times 0 plus c. 11 squared is 121, minus 11 is 110. And all of this goes to 0. And so we end up with a particular solution of y squared minus y is equal to 1/3 t cubed plus 5t plus 110. And so this is the particular form or particular solution, but it's written in implicit form. If you recall, explicit form is where we have y equals stuff. Implicit form is where we just have an equation, which is the solution. And it doesn't actually have to be solved for y. Again, you could solve this for y if you wanted to, but you would get pluses and minuses floating around, and it's not going to be very nice because this is going to be some odd-shaped curve. In fact, if you want, we could graph this curve using our good friend Desmos. Let's see what that solution curve looks like. Let's share the screen and go to our good friend Desmos. Y squared minus y equals 1/3 t cubed plus 5t and then plus 110. Oh, it doesn't like solving this. That's interesting. Wonder if maybe I need to make it so that it's x's so that it feels more comfortable doing it. There we go. So I just converted the t's to x's so that Desmos felt a little bit more comfortable graphing this. This is what the graph of it looks like. Like I was mentioning, this is not a function, and so writing out the equation in explicit form might not make that much sense. But you could do it. I mean, you could complete the square on the left side and you'd get a square root on the right side, and then you'd have a plus or minus and then a shift, and it just would not be very pretty. But that's the idea behind separable differential equations. This last one, again, it's more of the same. You just separate out the variables and then integrate and you're good to go. Wouldn't it be nice if everything was separable? What a shame. Turns out Math 420 is differential equations. And it is a course devoted to learning different techniques for solving differential equations. This separable technique is the one you usually learn the first week of the semester. The one you learn the second week of the semester is this next one. And it's for a first order linear differential equation. And let's just write this differential equation out, and then I'll show you how we develop the solution to it. And so it would look something like dy dt plus p of t y equals q of t. And so this is a first order linear differential equation. And what makes it linear is we just have a y term alone. If you want, you can kind of think of this as augmenting the slope of the y, but it's not really a good way of interpreting it. This is a differential equation which has a derivative, and then it has the y term there as well. The functions of t can be any functions we want, and it will still be considered a linear. We cannot have any other functions of y involved. The only y term involved in this entire thing is this one y value. And to solve this, Well, it's not separable. If we were to move the PTY over to the right side, it's very unlikely that we would be able to solve it unless the P of t and Q of t are very nice functions. And so instead, we want to think about structures we've seen which involve a derivative and a function. And the main structure that comes to mind is the product rule. The product rule, if you remember correctly, is u times v. When we take the derivative of this, d dt of this, we would get u times dv dt plus du dt times v. And that's our product rule. It's the derivative of one times the other, and then the derivative of the other times the one. Well, if you look over here, we almost have this structure in place. Not quite, but we almost do. And so if we look at this, we have this term here and this term here, which kind of are like the dv dt and the v. And so if this p of t term were the derivative of whatever's here, we'd be good. The problem is we don't actually have anything here. And so what we do is we multiply the entire equation by a new function. And we call the function mu of t. And so we multiply mu of t by this, giving us mu of t times dy dt, plus mu of t times p of t times y. And then we get mu of t times q of t. And what our goal is our goal is to make it so that this left side mimics this product rule. And so we want this to correspond to our v and our v prime. We want this to correspond to our u and our u prime. And if we can do that, then we can rewrite this entire left side as a derivative. It would be ddt of u times v, just like we have ddt of u times v. This would be the derivative of mu of t times y equals mu of t times q of t. And here's where the magic happens. This left side is a derivative with respect to t. The way that we undo a derivative is we integrate. And so if we integrate both sides with respect to t, then the left side is just going to become mu of t times y. And then the right side is going to be very gross. The integral of mu of t times q of t dt. And then we're going to get a plus c term that floats around because we still need that plus c. To solve for y, we then just have to divide by mu of t. And notice this is the only y term that's here. And so this is the general strategy to solve a linear differential equation. Here's the challenge, though. This only works if the derivative of mu of t is equal to mu of t times p of t. And so we would need some factor, some integrating factor, which will do that. And we just so happen to have one. We call it the integrating factor. The integrating factor. And the integrating factor is always just going to be e to the integral of p of t. So mu of t is equal to e to the integral of p of t dt. Now, it turns out this will work no matter what antiderivative of p of t we use, And so in this case, we can just let the c be equal to 0. And so we just need to find the antiderivative of p of t and ignore our c values for that. As an example, if p of t were equal to, how about sine of t, then our mu of t would be equal to e to the integral of sine of t. And the integral of sine of t is a negative cosine? Yeah, that sounds right. And then we don't even have to worry about the plus c term. And so that's the general process that we're going to be using. And if you want, as always, I've got this process outlined in the lecture notes. And here is the integrating factor. The integrating factor is just e to the integral of p of t. Let's try an example and see if we can figure this out. Oh, this looks like a good one to start with. Let's do number 1. So number 1 is dy dt is equal, or dy dt minus 3y is equal to 1/2 e to the t. So in order to figure this out, the first thing we need to do is figure out what our integrating factor is. And our integrating factor is just going to be the integral of whatever is in front of this y value. And so this is our p of t. Then this over here is our q of t. And our mu of t, our integrating factor, is going to be equal to e to the integral of -3. And e to the integral of -3 becomes e to the -3t. Now we're going to take this e to the -3t and we're going to multiply it by all 3 of these terms. And so doing that, we are going to get e to the -3t times dy dt minus 3 e to the -3t times y equals 1/2 e to the t times e to the -3t. Now, notice we did this so that this left side is a product rule, and we can verify that this is a product rule. If this is our v, this is our v prime. If this is our u, well, the derivative of e to the -3t would be -3 e to the -3t. So that means that this left side is really d dt of u times v. Our right side we can clean up a little bit because we have a 1/2. E to the t times e to the -3t is going to give us an e to the -2t. And now we have a derivative, and to undo a derivative, we need to integrate. And so we will integrate with respect to t. Integrating with respect to t. Well, on the left side, the derivative just goes away. So we're left with e to the -3t times y. On the right side, well, the integral of e to the -2t is going to have a -1/2 come out. So we should get a -1/4 e to the -2t. But let's just double check real quick. When we take the derivative of this, the -2 comes down and we are left with a 1/2 e to the -2t plus c. While we did not need the plus c when we were finding the integrating factor, that was only because any plus c term here would work. Here, we do need the plus c because we're still solving a differential equation, which means integrating, and well, this plus c is going to give us the family of solutions. Our last step is we need to get our y alone. And one approach is we can divide everything by e to the negative 3t. But there is a nicer approach to this. And the nicer approach is to multiply by the opposite sign of the exponent. Because if we multiply everything by e to the 3t, well, e to the 3t times e to the negative 3t cancels. So this is just a nice shortcut to get things a little cleaner, quicker. So now on the left side, we're going to have y all alone. And on the right side, we're going to have negative 1/4. E to the negative 2t times e to the 3t gives e to the t. Plus c e to the 3t. That's our general solution. And that's how you would solve this starting differential equation using the method of integrating factors. Let's do one more for good measure. Looking at these, they're all more or less the same. With this one, it's going to be integrating the 2t, which we can do. This one's a little interesting because we'll be integrating by 1/x. And so we're going to have a lot of interesting things cancel out. This one has just got the constant in there, but maybe we'll do an initial value problem. 6 is an amazing question. It is by far my favorite math problem in this entire course, but it takes a little bit of practice and a little bit of time. So maybe we will do number 5 instead, because 5 is also a very fun and interesting one. And so let's try number 5 and see what we get. 5. dy dt equals e to the t y minus e to the t. And y of e is equal to 0. And so this is an initial value problem. Our initial value is y of e equals 0. And so when t is equal to e, our y value is equal to 0. That's kind of interesting because often we'll see y of 0 equals something, but this is kind of flipping the script on that. There we go, a little coffee helps. And so first things first, we need to get this in the proper orientation. Now we need to get it so that it's set up so that it looks correct. And so that means we should move our e to the ty over to the left side. That would give us a dy dt minus e to the ty is equal to negative e to the t. Now, you might already notice that something weird is going to happen, but let's see what happens. When we find our integrating factor mu, well, mu of t is going to be equal to e to the integral of negative e to the t, which is just going to be e to the negative e to the t. And so we're going to need to multiply e to the negative e to the t by all 3 of these. And when we do that, we get e to the negative e to the t dy dt minus e to the t e to the negative e to the t times y equals negative e to the t e to the negative e to the t. Now, looking at the left side, we know that this should be a product rule. And we should verify. This is our v, this is our v prime. this is our u, then this is our u prime. And so now we can rewrite this as d dt of, let's see, e to the negative e to the t times y. The right side is going to be just negative e to the t, e to the negative e to the t. And now, just like before, we need to get rid of our derivative, which means we are going to need to integrate on both sides. Now, when we integrate on the left, we know that our derivative just cancels out. And so we're just going to be left with e to the negative e to the t times y. And so we get e to the negative e to the t times y. On the right side, integrating this might look daunting, but it turns out we've actually already done it. Notice that this negative e to the t, e to the negative e to the t is the exact same term we had up here. And we said this is the derivative of e to the negative e to the t, which tells us the antiderivative of this is just going to be e to the negative e to the t. Plus c. Now we have to actually figure out what our c value is, because this was an initial value problem. And so to figure out what our initial value is, oh, sorry, I guess before that, we should actually solve for y. And so let's solve for y first. And so to solve for y, we can multiply everything on both sides by e to the e to the t. Because when we multiply by e to the e to the t, e to the e to the t times e to the negative e to the t cancels out. And that leaves us with just y. For this one, e to the e to the t times e to the negative e to the t is just 1. And then we have c, e to the e to the t. But now y of e is equal to 0. We can use this to figure out what our constant c is. And so we can plug it in. We're going to get 0 equals 1 plus c e to the e to the e, because we're plugging in the e where we had a t. Solving for c, we can subtract the 1. So we'll get negative 1 is equal to c e to the e to the e. And then in order to move the e to the e to the e over to the left side, we could kind of use the same trick we had over here where we multiply each side by e to the negative e to the e. Because e to the negative stuff and e to the stuff are going to cancel each other out. And so that tells us that our c value is equal to negative e to the negative e to the e. Now we can plug this in. And when we plug that in, we get our final answer, our particular solution of y equals 1 plus negative e to the negative e to the e times e to the e to the t. And I think that one's just the right amount of silly, because it is kind of a fun and silly problem. This one is really just a precursor towards the next problem, which I'll let you folks do on your own. But the next one is just an incredibly fun and silly problem. Number 6, e to the negative t times y prime plus e to the t times y equals e to the t, and y of e equals e. It is an amazingly fun and silly problem. as mentioned, your homework shouldn't have any of these in the online portion. Often I'll assign a PDF which has practice problems for this. And so keep an eye out if you want for that. But this is just a secondary approach to solving differential equations. Since your book does not include multiple approaches to solving differential equations, I thought the method of integrating factors was an important one to show. Separable equations and method of integrating factors are really the two foundational ways of solving simple differential equations. Note, did you know that Wolfram can solve differential equations too? Is there anything it can't do? And then I have this graph, which is a little daunting, but hopefully it's not too scary. That's going to be coming up very soon. But let's continue on. And so now we have solved some differential equations. We know how to solve some differential equations. I think that means that it's time that we tried something completely different. And the completely different thing we're going to be doing is what 7.5 is about. And that's parametric equations. Parametric equations is something which should really be taught in a pre-calculus course, but pre-calculus isn't a prerequisite for this course, and oftentimes you don't need it until you get it right around here. And so our textbook introduces it in 7.5. The idea with parametric equations is sometimes we have curves which we cannot really well represent using just x and y. And so we need other things to represent it. Ideally, we want to figure out how things move with respect to time. And so, for instance, if you're thinking about how a mosquito would move throughout the air, well, that's going to be a function of time, but it's also going to have an x, y, and z value associated with it. And so we could say, what is the x, y, and z direction at a particular time t, and try and create a model for that. We're going to be doing something similar to that, but we're only going to be dealing with two variables for now, x and y. And graphing these things really isn't that difficult. It's just new. And so let's try one and just see what it looks like. And we'll just start with number one and see what it looks like. And so x of t is equal to t squared minus 1. Y of t is equal to 3 minus t. And then we're told a range for t. And so 0 is less than or equal to t is less than or equal to 3. Now, the way that we would approach a graph of something like this is really we would say this x of t and y of t is going to be giving us an ordered pair at a particular time t. And so we can create a table of values, just a standard old table of values, where we'll have our t value, but then we're also going to have an x value, where x is given by t squared minus 1. And then we're also going to have a y value, where y is equal to 3 minus t. Now, the values for t that we're going to be plugging in are only going to be going from 0 to 3. And so we might start with 0, and then we could go by every half if we wanted to. So 0.5, 1, 1.5, 2, 2.5, and 3. As you might expect, the more values we choose, the better the graph will look. But this should give us a really good idea of what the graph looks like. So now we just have to plug these values into each of these equations. And so for 0, if we plug 0 in for t, x will be equal to 0 squared minus 1. 0 squared minus 1 is negative 1. If we plug 0 into this one, well, y is equal to 3 minus 0 is 3. And then we just have to do that for all of the remaining values. The y value is actually going to be pretty quick. So let's do that one very quick. And so we get 3, we will get 2.5, we will get 2, we will get 1.5, we will get 3 minus 2 is 1, 3 minus 2.5 is 0.5, and then 3 minus 3 is 0. This one might be a little bit trickier, probably not a lot trickier, but a little trickier. Let's do the integer values quickly. And so we would have 1 squared minus 1 is 0. 2 squared minus 1 is going to be giving us 4 minus 1 is 3. And then 9 minus 1 is 8. For the others, I'll grab a handy dandy calculator, just so I'm not really willing to think too hard about it. 0.5 squared minus 1 is negative 0.75. 1.5 squared minus 1 is 1.25. Then we have our 2.5 squared minus 1 is 5.25. So these now form ordered pairs. In that, we can think of this as corresponding to the x value, and this as corresponding to the y value. We can do that for all of these. And I'll just throw a little comma in there. And these are our ordered pairs, which we are now going to graph. Looking at this, it looks like the x direction is going to be a bit longer. And so let's actually draw this out so that it has our x values. So 1, 2, 3, 4, 5, 6, 7, 8, and negative 1. Then our y values will go 1, 2, 3, 4, 5, and down 2. And now we just have to go through and plot all of these points. So negative 1, 3, back 1, and up 3. There's our first point. Negative 0.75 and 2.5 would be right around here. 0, 2, that's right there. 1.25 and 1.5, that would be right around here. 3 and 1, 1, 2, 3, and 1. Then 5.25 and 0.5. So 1, 2, 3, 4, 5.25 and 0.5. And then 8 and 0. So 8 and 0, 1, 2, 3, 4, 5, 6, 7, 8, and 0. There we go. Last thing to do, connect the dots. So we know we're starting here and we are ending here. And oftentimes with these, it's not clear the direction that you're going. And so you'll often add an arrow on there to show the direction that things are going in. And so here we're starting at time t equals 0 at this point. And then as we get to time t equals 3, we end at this point. And this is the curve which we are following. That's the idea with parametric equations. Hopefully it's not too bad. Really at time t, it's just telling you what the different values are. Now here's the fun thing. Desmos is amazing at these. And so let's pull our good friend Desmos up. The way you would do a parametric equation in Desmos is you would actually just do the ordered pair, and then you would say x is going to be equal to t squared minus 1. And y is going to be equal to 3 minus t. And then we can just set this to go from 0 to 3. And there is our graph. Let's zoom in a bit. There is our graph. And that's it. That's really all that a parametric equation is doing. Parametric equations can do some very cool things, though. For one thing, this first example that we did was a pretty boring example, because these things can get very, very interesting. Take, for instance, the unit circle. If we were to do cosine of t, comma, sine of t, And let's say that we go from 0 to 2 pi. We get ourselves our good friend, the unit circle. Oop, let's zoom out just a hair. And sure enough, if you plug in values when t is equal to 0, you start out at 1, 0. And so you would actually start out at this point. We could even create a slider for a variable t. Let's say t is equal to 0. Let's make it so that it goes from 0 to 2 pi. And then I would like this animation to just go forward. That sounds good. And now we can create a point on here given by cosine of big T, comma sine of big T. And this will show how, with respect to time, this point is going to be going in a circular motion. And this is all just done parametrically. This first one, the cosine of t comma sine of t, is just the general equation. And then this is showing how it progresses along that at various times of t. Now, I believe we could even make this a little bit easier by saying, let's let x of t be equal to sine of t. And then we will let y of t be equal, or sorry, let's let x of t be equal to cosine of t. And y of t be equal to sine of t. And then we'll just create a general thing, which is x of t, comma, y of t. Oh, is it not going to let us do that? It doesn't know what to do with that. So we'll just say this is x sub 1 and y sub 1. And this will be x sub 1 and y sub 1. There we go. Then we'll make this go from 0 to 2 pi. And now this is basically doing the same thing we were doing, but this is also showing how x of t changes with respect to time, as well as how y of t changes with respect to time. And we can create the same dummy variable of t. And we'll say that t goes from 0 to 2 pi. And then we can also create the parametric equation, which shows where that point is. And so we could say x sub 1 of big T, comma, y sub 1 of big T. And now again, we can show how this moves around. The benefit of doing this, oh, and I want this to just be going in one direction. Oop, let's just go forward. There we are. So the benefit of doing it like this, where x1 and y1 are written out like this, is because now we can actually change what these functions are. And interesting things happen when we start to change what the values inside of these cosine and sines are. For instance, if we made this a cosine of 2t, we get a parabola for some reason, a sideways parabola. When we make this a 3t, we get one of these. If we make both of them odd, we start to get some very interesting paths. And these are just going to keep cycling over and over and over again. And we can get them as complex as we want. So let's say that we make this a 7. And we can make this a 9. And we just see that this particle is just going to be zipping around this entire thing as fast as you want. And it's going to cross all of these different curves. This is for cosine and sine. We could do it with any functions if we wanted to. We could throw square roots in there. We could make it so that we had semicircles floating around. There's lots and lots of different things we can do with this. But this is just one of those things where we can actually show what a path would look like by using these parametric equations. Perhaps an easier one might be something like t squared minus 2t. And then maybe this one will be equal to a square root. Square root of e to the t. And then let's make it so that it is a minus 3. And so we get a curve like this. Depending on the type of thing which you're trying to model, you can use parametric equations to model any curve. And that's really the big idea here. Looking at the examples that we have here, we have the cosine t and sine of t, and then we have the square root of t and t. Neither one of those is particularly interesting, but we can model just about anything we want. And so if we want to say that in the x direction, we're going to have a sine function, but in the y direction, we're going to have something which is looking more logarithmic. And what if we want to see what it looks like as we go out to 100? Well, we end up getting a squiggle, which will look something like this. And we can ask the question of why does it look that way? And those are important questions to ask. But we can also make it so that this will shift around. And so if we wanted to add a t to this, or add a t to this, well, now we have that similar structure, but now it's kind of going along the line y equals x. For our purposes, we're not going to spend too much time worrying about parametric equations, because we're really using parametric equations to develop the next idea. The next idea being, what do we do when we have systems of differential equations? And systems of differential equations are the extremely important thing. Systems of differential equations are used to model everything. That's what we were saying at the very beginning of today's lecture. The easiest way to understand them is in terms of parametric equations. But here's an example of a system of differential equations. And so as an example, the following is a system of differential equations which could model one species which has unrestricted growth and a second species whose growth is related directly to the seasons and inversely to the population of the first species. That's what this system looks like. Notice, though, that there's a t variable in here, which means that this is tied to time. And it's tied to time because of the seasonal aspects of it. To make it an autonomous system of differential equations, we need to get rid of the time variable. And that's the type of model that we really want. And here is an example of one. This is the Lotka-Volterra predator-prey model. It is a very, very standard differential model which shows how rates of change can be used to model population dynamics. This is the introduction one. And we can explain where all of these terms are coming from and why they exist. But for now, let's just see if we can understand what it's saying. It says dr dt is equal to r, which is just some scalar, times population r, big R, minus a times big R times big W, where this big R represents rabbits and the big W represents wolves. Notice with this, if our rabbits population is really big and our wolves population is very small, then this RR term is probably going to be the dominant term. And that's where we would see exponential growth. But notice our wolf population is tied to that. And so our wolf population has a negative KW and a plus BRW. And so if our rabbit population is large, well, this term is going to dominate, which means our wolf population is going to start to increase. And we can get some interesting results from that. Let me do an aside real quick and show you how these differential models are formed and how we can understand these differential models. Because one thing your book doesn't really go in depth into is understanding how these differential models work. And so let's stop the share and we'll come down to the whiteboard. And let's suppose that we have two populations, and we will keep it with rabbits and wolves just for an arbitrary sake. Let's say that we have R prime and we have W prime. Now, if we want to create a simple differential model for these, there are certain terms which we would expect to see. And so we might expect to see terms of the form R, of the form W, of the form RW, and of the form R squared. And same for the W term. We would expect to see terms of the form R, of the forms W, of the form RW, and of the form W squared. Each one of these terms has a different meaning and a different representation. And we can go through and show exactly what they correspond to. And so let's start. Let me shift this over here so we can just keep this here. Let's start with a term that looks like this. R prime equals AR. This term represents exponential growth, assuming the A is a positive value. And it represents an exponential decrease if the A is a negative value. And so this is saying the rate of change of the population is proportional to the population of rabbits, either in a good way or a bad way. This gives us unrestricted growth. And so this is saying there is nothing that is going to slow these rabbits down. They are going to grow exponentially forever and ever and ever. Exponential growth is very rare. It is almost never going to occur. Instead, what we'll often see is we'll see some limiting parameter. And that's where we might see something like this. R prime is equal to, oh, this represents exponential growth, by the by. And so this next model is where we see a limiting factor. And it might look something like this. AR and then B minus R. Sometimes it's written like this. Sometimes it's written like this, just AR minus B R squared. And that's where we'd get an R squared term from. Of course, this would be an A times B, but we could ignore that for now. This is creating a limiting factor. And so this is logistic growth. Notice from this second equation, if we have a ton of rabbits, just a ridiculous amount of rabbits, this R squared term is going to overtake this R term. Usually this B value or this value in front of the R squared is a very, very tiny number. That way, for smaller values of R, this term is the dominant term, but for larger values of R, this term overtakes it and becomes dominant. If we look at this equation, this first equation here, if we were to say that A is equal to 0.1 and B is equal to 1,000, well, we can think about what the phase diagram for this is going to look like. The phase diagram for this is going to have an equilibrium at 0 and an equilibrium at 1,000. If we are less than 0, then everything's going to be positive, but that doesn't matter because if this is our rabbits population, it's saying we have no rabbits, so it doesn't really make sense to have things down there. If we are between 0 and 1,000, we will notice that this term's positive, this term's positive. And so this would be positive. I had this sign backwards. This would be a negative down here. Sorry about that. And then up here, we would also get a negative. And so what the graph of this will look like is something like this. Basically, no matter what our starting population is, we would see that our population grows to roughly 1,000, and then it stays there. If you start with a population which is more than 1,000, it's actually going to decrease in an exponential way towards that 1,000. This is basically the limiting factor for this logistic growth. It's saying that we are going to be approaching this 1,000 mark, and that's the most that we're going to see. And this is a much more common model because if you're talking about any species, it will grow up to a point, but eventually it's going to run out of resources. And so it can only grow up to a certain point and then it stops growing. And that's what this is all about. The other type of term that we will see, though, is we will see terms which involve both variables. And so let's say that we have an R prime equals an AR minus a BR squared. And then let's throw in a minus CRW. Well, in this case, this term is saying, well, these two terms are saying what happens to the rabbit population when you have no wolves. Because if you have no wolves, then W is equal to 0. And this term does not affect things. And so the rabbit population when we have no wolves, in this case, would be considered logistic. Adding this CRW term, though, is saying what happens when you do have wolves. And this is really talking about the interaction between rabbits and wolves. And so what happens when rabbits and wolves interact with one another to the rabbit population? And so the rabbit population is going to have a negative effect when rabbits and wolves are interacting. Because when rabbits and wolves interact, wolves eat the rabbits and the rabbit population decreases. And so that's what this is telling us. This is telling us that the interaction between rabbits and wolves has a negative effect on the rabbit's population. These three ideas give us the tool set needed to create a number of different differential models. And we can create one for rabbits and wolves real quick. These are all of the possible terms. Let's see which ones make sense. And so this R is representing what happens to the rabbit population, or the rate of change of rabbits when we just have rabbits. And we know that's going to cause an increase in the population of rabbits. This term is saying what happens to the rabbit population when there are no rabbits and only wolves. Well, if there are no rabbits and only wolves, it's not going to affect the rabbit population because there are no rabbits. This term is saying what happens when the rabbit and wolf population interact with one another. And like we mentioned, when rabbits and wolves interact, it has a negative effect on the rabbit population. So we would expect this to be negative. And then this term is saying, when we're thinking about rabbits, should we be concerned about logistic growth? And realistically, we should be. And so we will say minus C R squared here. For the wolf population, well, this term is saying what happens to the wolf population when we have only rabbits and no wolves. Again, if we have no wolves, there's no effect on the wolf population because it's just going to stay 0. This is saying what happens to the wolf population if we have only wolves and no rabbits. And if we have only wolves and no rabbits, the wolf population is going to decrease because there is no food for them. This term, the RW term, is saying what happens to the wolf population when we have rabbits and wolves interact with one another. And that has a very positive effect on the wolf population. And then our last one is, should we be taking logistic growth into account here? And in this case, we probably shouldn't be worried about logistic growth because we did not have exponential growth for wolves to begin with. And so this should not be included. Basically, the logistic growth of the rabbits is what's going to be hindering our wolf population. And so this is a standard predator-prey model. The Lotka-Volterra predator-prey model is basically this entire thing, but it does not include this term here because it says we're not going to worry about logistic growth when we're talking about our populations. And that's a fine assumption to make if they want to. But that's how we can understand all of these differential equations, all of these systems of differential equations and what these models represent. This is the simplest model. You can get much more complex and you'll see much more complex models out there. But this gives us a really good understanding of the structure of differential equations and what they're representing. And again, when you're talking about anything, we can model it. If you're talking about tumor growth, well, we can ask how normal cells interact with tumor cells, as well as immune cells, and create a very strong differential model just based on those three types of cells. And I've seen some fun models using that. But this is the idea with an autonomous system of differential equations and how we can understand them. Next idea is, how do we actually graph them? Because ideally, we want to be able to see these things. We want to be able to see how these interactions affect one another. And kind of like before when we were doing the phase diagrams, we can do something similar with these systems. And so if we have x prime of t and y prime of t, we can create a graph which will show us what the behavior is. Basically, we'll be told how things are moving in the x direction and how things are moving in the y direction. And so with this example, x prime of t is equal to x plus y, and y prime of t is equal to x squared minus 4. We can create a chart which will show the directionality of the x direction and the y direction on a large set of points. So let's create a 3x3 grid and see how quickly we can create one. 1, 2, 3, 1, 2, 3, and 1, 2, 3. And so in this case, we are going to be looking at every single point, and we're going to be asking, how are things affected in the x direction and how are things affected in the y direction? And it's going to become a very complicated vector field very quickly. I don't know how many I want to do for the video, but we shall see. And so looking at this, x prime of t equals x plus y. This tells us what the rate of change is in the x direction at all of these points. So let's choose a point. How about up here? This point up here would be 2, 3. Well, at the point 2, 3, this is saying that it's going to be going 5 in the x direction. And we could draw an arrow that goes out 5 units if we wanted to, but that's going to be pretty far out there. In the y direction, it's x squared minus 4. Well, x squared minus 4 is going to be equal to 2 squared minus 4, which is 0. And so, is that right? Yeah, it's going to be 0. And so this is not going to be going in the x or y direction at all. Since we might not want to have an arrow that's going this long, often we will truncate it. And usually you'll see these arrows shortened so that they're 1 unit long or half a unit long or something like that. I will just show the arrow going in this direction. And we can then do that with all of the remaining points. And there's a lot of points. And so let's say that we do this one here at 3, 3. At 3, 3, we're going to be going 6 in the x prime direction. And so that's going to be going out here really far. But then we're going to be getting 3 squared minus 4, which is going to be 9 minus 4 is 5. And so we're going to be going 5 up. Since we're going 5 up and 6 across, it's going to be looking a little less than 45 degrees. And now we have to do this with all of the points, which does not sound fun. Sometimes what helps is to actually figure out where things are going to be flat. And so where things are going to be equal to 0. So notice with x plus y, this is going to be 0 along this line here. And so along this line, we know that it's going to be going 0 in the x direction, which means that it's only going to be going up and down. In the y direction, we can do the same kind of idea. And so we can say, when is this going to be equal to 0? And x squared minus 4 is going to be 0 when x is equal to 2 or negative 2. And so that means along these lines, it's only going to be going to the left or to the right. Notice right off the bat, we now have 2 points where it's going 0 in the x direction and 0 in the y direction. This structure that we've just created gives us a way of approaching this, which is a little bit more advanced than testing every single point. And that's what null-clines are all about. And so let's share the screen real quick. I think I might have skipped to the next page since I didn't want to graph all of those points. But if we were to graph all of those points, we would get this vector field. And this vector field kind of shows off what all of the different points look like. And so we start to see some weird behavior where it starts to kind of spiral down and around. And then up here, it starts to spiral downward, but then it starts to go upward for some reason. Same down here, we can see that it's starting to curve in an upward direction, and then it starts to go up and then down. And we could figure out all of these points to graph this. But that is a tremendous amount of work, especially when we actually have a tool which will do it for us. The tool is called p-plane, and there are other tools out there. But p-plane is a tool which will graph these types of differential flows. This one that we start with here is 2x minus y plus 3x squared minus y squared plus 2xy, and x minus 3y minus 3 times x squared minus y squared plus 3xy. That gives us an arrow system, a vector field, which looks like this. And we can then click on it, and it'll show us what the curves would look like. This is very similar to the D field program we were using before. But notice, interesting behavior happens depending on where you start. For the model that we're doing, well, we were doing x prime of t is equal to x plus y. So we'll type x plus y in. And then y prime is equal to x squared minus 4. And then our window would be from negative 3 to 3, and negative 3 to 3. Maybe we'll go negative 4 just to make it a little bit easier to see the spirals that pop out of this thing. There we go. And so notice we have something up here which is starting off kind of steady, but then it starts to spiral out and around. And we can do the same over here and see that there's another point down here where things are kind of spiraling towards it and then away from this point. Right around here is where we get a point which isn't moving. This diagram is called a phase portrait. The phase portrait is when you have all of the arrows figured out. In particular, you show what the phase lines look like. And our goal is going to be to figure out how to graph these things, though much of that is saved for chapter 10. For our purposes, instead, we're going to focus on the idea of how to create these phase trajectories using something called null-clines. Oh, and here's what the graph looks like. And I also have a link to p-plane, though I noticed that p-plane might be under new ownership. It's a free app, but it looks like they're trying to move towards using MATLAB. So I might need to find new programs to use for these. But I'm interested in looking at the null-cline approach, because the null-cline approach is going to be an easier way of understanding how to graph these things quickly. And so let's stick with the exact same graph, but instead of doing it point by point, let's try and figure out how to do this using null-clines. So as mentioned, a null-cline is what you have when you set one of these differential equations equal to 0. And so if we set it equal to 0, that tells us that it's going to be going flat in that direction. And so x prime of t equals 0 and y prime of t equals 0 is what we're going to be looking for. And so let's set x prime equal to 0 and y prime equal to 0, and we'll see what graphs we get. And so first, we'll do our x null line. So our x null line is when we have x prime equal to 0. And if x prime is equal to 0, we have x plus y is equal to 0. And if x plus y is equal to 0, that tells us that y is equal to negative x. Well, y equals negative x is a graph which just looks like this. Goes at 45 degrees. And so this would be our x null line. Now note that if it is going 0 in the x direction, that means the only direction that it's going to be going, I did that line very bad, sorry about that. The line y equals negative x would look like this. Clearly, I need to go back to algebra 1 so that I can graph stuff like that. But since the x null line has the property that it's going 0 in the x direction, the rate of change in the x direction is 0, that tells us that we're not moving left or right on this line. On this line, we are only going to be going in an up and down direction. And so that means curves could be coming into these and then going out from them. But on this line, it is going to be staying in an upwards and downwards direction. To do the y null line, we do something similar. So the y null line is when y prime is equal to 0. And to figure that out, we would say x squared minus 4 equals 0, which tells us that x is equal to 2 or x is equal to negative 2. And so when x is equal to 2 or negative 2, we have our y null lines. And much like the x null lines, the y null lines have the property that the rate of change in the y direction is 0, which means you're not going up or down on these lines. The only direction we could be going is left and right. And so we can show that these are going left and right on those lines. We're not going up or down at all. We can then see that we have a couple of points where things are fixed. They are not moving at all. These points are called fixed points, and we can figure out exactly where they are. Because we know that y needs to be equal to negative x, if x is equal to 2, I'll just write fixed points. If x is equal to 2, then y is equal to negative 2. And that's what this point should be representing, though it looks like I might have my scaling a little bit off there. I could probably fix that real quick just by adjusting that so that our axis goes there. There, perfect. And our other one will be when x is equal to negative 2. And when x is equal to negative 2, our y value is going to be equal to positive 2. So this is our negative 2, positive 2. This is our 2, negative 2. And those are our two fixed points. At those points, things are not going to be moving. To figure out the directionality of all of the phase lines, all of the curves which will be inhabiting this, we would do test points in each one of the regions. Now, I believe your homework stops you at this point. I believe the chapter 7 homework says, just graph out the null lines and we are good to go. Find the fixed points and we're set. But if we want to go a step further and do the type of stuff we'll be doing in chapter 10, what we would do is we would choose test points from each of the regions. And in this case, we have 6 different regions. And so let's just choose a test point in each one of those regions. And now we want to figure out how things are moving in the X direction and in the Y direction for each one of those regions. And so let's start with in the X direction. And so in the X direction, we know that we have this X null line. This is the only place where it's equal to 0. That means everything above it is either going to be positive or negative, but it's not going to be 0. And same with everything beneath it. It's going to be positive or negative, but definitely not 0. And so let's determine the signs. And let's do a test point up here. If we're at like 10, 10, we're definitely in quadrant 1, which means we are on this side. 10 plus 10 is 20. So that means that we are going to be going in a positive X direction if we are in this region. And it turns out everything on this side of the null line is also going to be going in a positive X direction, including on the null lines. If we are on the other side, like let's say we were at -10, -10, well, that's going to give us a negative X prime. And so that tells us that everything is going to be going in the negative X direction. For the Y direction, same idea. But now notice we have 3 different regions when we are just looking at the Y null line. If we are somewhere in this central region, let's say that we are at 0, 0. At 0, 0, we would get 0 squared minus 4, which is -4. That tells us that we are going to be having negative Y values or negative Y prime values for everything in this central region, including on this X null line. When we were out in this region, let's say that X is equal to 10 or something, we get 10 squared minus 4, which is a positive value. And so we would see things which are going in an upward direction over on this right section. Over on this left section, same idea. If we were at -10 in the X direction, we would get 100 minus 4, which is very positive. And so that shows the directionality that we would expect on those null lines. This tells us how things are going to be moving. And if we want, we could then just choose some random points and follow the arrows. And so for instance, if we started close to this fixed point here, well, we know that we are going to be going in a downward and to the right direction. And so eventually we're either going to cross this orange line or we're going to cross this green line. Let's suppose that we cross this orange line. Well, as soon as we cross this orange line, we're going to be going down and to the left, which is going to send us towards this green line. As soon as we pass that green line, we're going to be going up and to the left, which is going to take us up here. But as soon as we cross that, we're going to be going up and to the right. And as soon as we cross that, we're going to be going down and to the left again. Let's suppose that this one does cross this line. After it crosses that line, we see that it's going to be going up and to the right. And that gives us the curve that we would expect to see. Now we could try another test point. Let's say that we started somewhere over here. We started down in this region. We're going up and to the left. And so we'll see something coming up in this direction, but then it's got to cross this line. If it crosses this line, well, then it's going to be going down and to the left, which means it's going to be coming down in this direction. From this side, it could have been coming up and maybe it crosses this orange line. If it crosses the orange line, well, then it's going to be going up and to the right. And at this point, we have the general shape for what this curve is going to be doing. No matter where we choose, it's going to be following these general guidelines. So we're going to see curves which come down, hit this, and go up. We're going to see curves which are coming from here. Maybe they're going to be spiraling out a little bit more. And then once it comes there, it might cross down here, at which point it will start to curve down, and then it'll start to go back up. And then our goal is just to kind of fill this in with as many lines as we feel fit to. We can create a pretty good idea for what this curve is going to be doing. We're just following the arrows. And then add arrows to your phase lines so that you know the direction that they're going. And this is what you do in chapter 10. In chapter 10, you'll be learning ways to better do these types of graphs. For now, we're mostly just interested in the null lines, but it's really easy to extend the null lines to actually get these graphs, which show how these two populations react to one another. And if we want, again, we can use d-field or p-plane to graph what that looks like. But that's the general idea behind this idea of phase lines and how we can use the null lines and fixed points to figure out what these things look like. Here I have this problem that we just did all worked out if you want. And so I have the phase lines for it graphed out on here so that you can see where they are, and you can see the arrows which are pointing in the directions that they're going. And it also has the two fixed points mapped out on them also. From there, we can then do all of the phase lines because the phase lines will show us how all of those curves are connected. And I have a few additional practice problems here. Let's just do one more, just because they're basically the same idea. It's just you need lots of practice to get good at it. And so let's do that first one. Make sure that we can do our null lines, and we will then have our graph. There we go. And so with this problem, we are going to be saying x prime of t is equal to y times x squared minus 1. And y prime of t is equal to x plus y. That's convenient. We've seen that one. And so when we go to graph this, we'll create a Cartesian coordinate system, which let's just go out to like 3 again or so. 1, 2, 3. 1, 2, 3. Well, that doesn't work. Let me rearrange it a little bit. 1, 2, 3. 1, 2, 3. 1, 2, 3, and a 1, 2, 3. That should be sufficient for our purposes. And so to figure out our null lines, we start by setting these equal to 0. And so when x prime is equal to 0, we're going to get either y is equal to 0 or x is equal to plus or minus 1. And so y equals 0 is just going to be a line down here. And x equals 1 would look like this and this. These are our x null lines. And so remember, on our x null lines, we're not moving in the x direction. We can only move in the y direction. That tells us that on this one, the y equals 0 one, we're just going to be crossing it straight away. But for these two, something more interesting happens. Since we can only go up and down on these curves, that means that we can basically never cross these lines. Because if we were crossing these lines, that would tell us that our rate of change in the x direction was non-zero, but we know it is 0, and so we can't move past these lines. For our y null lines, same idea, but now it's x plus y equals 0, which tells us y is equal to negative x. We've seen that one before. Looks something like this. And on the y null line, we know that we are not moving in the y direction. So that means that we can only go left and right. And now we just have to figure out where our fixed points are and then figure out what's happening in each region. So in this case, our fixed points are where the green and the orange lines cross, and they cross at 3 points. At -1, 1, at 0, 0, and at 1, -1. These 2 points here we would not include because only the x null line is 0 at these 2 points. The y null line is not 0, and so it's only these 3 points which are fixed points. And so all the interesting stuff is going to be happening around those 3 points. But now let's choose points in all of the other regions. So 1, 2, 3, maybe a 1, 2, 3, 4, and a 1, 2, 3. And we will figure out what is happening in each direction for those 3 regions. Let's start with the x direction. So the x direction we have broken up into 6 regions, actually. So basically ignore this line here, and we can figure out what's happening in each one of those regions. And so in this region up here, where the x and y are both positive and large numbers, we could say 10 squared minus 1 is positive, and this would also be positive. So this is going to be going in a positive direction. In this central region, when x is like 0, we would see that our y is positive and this term is negative. So that tells us we're going to be going in the negative direction here. Over in this region, when x is a larger negative value, we would see that it would go positive again. Down on the bottom side, the only thing that's going to change is the y value is going to switch to a negative. And so we could really just take all of these arrows above and just change the directionality on them. And then over here, it's going to be going in a negative direction. Cool. So there are all of our x directions. For our y directions, well, we know that we just have this one line. So everything above the line should have the same sign. Everything below the line should have the same sign. If we are at 10, 10, we know it's positive. And so that means that everything above the green line is going to be going in a positive direction. Everything below the green line, similarly, is going to be going in a negative direction. There, 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 there. And then we have all of the arrows figured out. And so we can start to ask questions about what the phase lines would look like. Again, this is what would be expected for the homework, is to figure out where the fixed points are, 3 fixed points, and figure out where all the null lines are, as well as some of the directionality. But now to finish it off, let's just choose an arbitrary point and figure out what the curves would look like. And so for instance, if we start somewhere here, well, we can see that we're going to be going up and to the left. If we cross this curve, it's going to start to go down and to the left. If it goes down and to the left, then it crosses this and starts going down and to the right. But as soon as we approach this line, we see that we cannot cross it because it's going straight down. So we're going to have an asymptote of sorts going down here. Same thing happens on the other side. We'll see that things will start to spiral around. So if we're here, it's going to be coming out and it'll cross this and it'll go up. And then as soon as it crosses that, it comes up here. And we get a curve like that. As we get closer and closer to this, we might notice that it starts to kind of spiral out from this. Oh, this will never cross. And so it looks something like that. And then as we come out further, we might get even more abstract shapes. We might cross here. But eventually, we're going to start to see just curves which are coming down, something like this. And it'll just fill up this entire region with these curves. And that's the general shape that we'll get in that central region, where everything is spiraling away from that central point. Over on the right side, well, if we start down here, we'll see some curves, and some of them will cross this green line, and some of them will cross the orange line. If we have some which cross the green line, once it crosses, it's going to be going down and to the left. So again, it's going to kind of approach this asymptote. It's going to go pretty steep as we get closer and closer. But then curves which come up here and go on this side of that fixed point, well, they have to keep going up and to the left. But as soon as it crosses here, we'll see that it starts to curve out and up and to the right. How steep it is, we don't know. But we know it's going to be coming up, hit this curve, and then it's going to start going up and to the right. Left side is going to be very similar. We're going to start to see curves which come down, hit this, and then go up. And then we're going to see some which come down, go past this fixed point, and then just go or continue going down until we hit this. And that gives us the general shape of this. I always enjoyed these. There's something just mindless and fun about them. It's like a paint by numbers. And this shows how these two populations are interacting with one another. In this case, it's a little bit more abstract because we're not talking about predator and prey. We're talking about just random formulas and showing how they can interact with one another. But let's verify that this is what it looks like using that program, P-plane. So let's see, here is P-plane. This equation was y times x squared minus 1. And our y was x plus y. And let's make it so it goes, well, we can keep it at -4, I guess. And if we choose some starting points, notice how we get this interesting spirally behavior in the center. And then out here, you can kind of see that behavior that I was alluding to. But it's definitely more pronounced here. Excellent. Now, if you want, this system also will show you the null lines if you'd like. And there we can see exactly the null lines. And so we can see the line coming down the main diagonal. We can see in red a line going up, and then over here going across. And this looks relatively similar to the graph that we did. It's just a little bit more accurate in this. You can see how things are moving as far as what speed they're going, what the curvature looks like, and it's a little bit more accurate than the graph that we did. But our graph versus this graph, they're pretty closely related, and they look pretty similar to me. And with that, that brings us to the end of today's lesson. And so when we think about what we did today, we did a lot of stuff. We finished chapter 7. And we even did some stuff beyond chapter 7, which I think was kind of good. And so we started with the idea of separable differential equations. And separable differential equations are fairly painless. I mean, as long as we can separate it, we can integrate, and we're good to go. We then did a more advanced technique called the method of integrating factors, which is what you use for a first order linear differential equation. And it's basically using the product rule to solve things, but using the product rule in a very interesting way. From there, we jumped to parametric equations. And the reason we needed parametric equations is we needed to have an idea for how we can model things which are going through space, how X and Y can be two different variables, both related to time. And that way, when we're dealing with population dynamics, such as X prime of t and Y prime of t, we can visualize how they are changing with respect to time and how they move with respect to time. And we did the parametric equations before we jumped into this idea of systems of differential equations. We also talked about the predator-prey model, and we went in depth into these models. I don't know that we actually showed the predator-prey model, though. If you want, here is the predator-prey model. And so we have predators, we have prey down here, and this is showing how populations of predators and prey will interact with one another, depending on how many of each you have. And this, again, has a number of different assumptions, such as that it's a closed system, there's nothing else interacting with these two populations, as well as what the starting conditions might be. But notice we get this interesting cyclical behavior out of it. And we can try and understand why that is. If we start with very few predators and very few prey, the prey population is going to see an increase. But as we see more and more prey, the population of predators is going to start to increase. But as the population of predators starts to increase, the population of prey is going to start to decrease. But as the population of prey decreases, the population of predators is going to also see a decrease. And so we start to see this cyclical behavior. We can do similar things for competition models. And this is also assuming two variables. What happens when you start introducing three or more variables, three or more populations? I remember when I was looking up Alzheimer's model, there was a model which involved, I think it was 11 different variables. If you have 11 different variables, each related to the other ones to create a closed system, it can be difficult to analyze and understand what's going on. And that's really what the next course is about. This course, we end with the idea of null clients and how we can use null clients to understand differential flows. And the idea of differential flows and phase portraits in general. We can use systems of differential equations to model everything. And once we have a model, we can understand the long-term behavior based on graphs like these and introductory analysis on the variables. The next step is really going to be doing a deep dive into understanding these models. And that's what Math 356 is all about. For now, though, we will leave you with this idea of systems of differential equations. We'll have an abundance of work to get done before the end of the semester. And so I wish you all luck.